Okay, we take on from the point that we left in our last meeting. At that time, we discussed when does a crack grow? What is the criterion for a crack to grow? Initially, we brought up the idea that an externally applied stress, results in a magnification of the local stresses at the root of a crack. And in fact, actually, if that crack is very sharp, the local stresses seem like they tend to go to infinity. But at the same time, we also discussed an interesting point, which is it's not enough to apply any stress for a crack to grow. There is a condition that makes a crack to grow. And we had a qualitative discussion that allowed us to understand the concept that a crack needs energy to grow, and that energy must be supplied from somewhere. And you may remember the example of the balloon with a pinhole in an inflated versus a mildly inflated situation, where in the latter the balloon may not break, but if the balloon is actually substantially inflated, then the presence of a pinhole will make it break. So in that case, there is energy stored in the compressed gas and in the elastically strained membrane of the balloon that can provide energy for the crack to grow. We will make this argument much more quantitatively for a crack by exploring the following example. We consider a body in two different discrete situations. On the right, you see the body loaded but without the presence of any crack. In this case, the material is uniformly strained, and there is an elastic energy stored in the material, which is simply the area under the stress-strain curve. And if you do a quick calculation here, that will be 1/2 sigma times epsilon, or 1/2 the Young's modulus times epsilon square, or 1/2 sigma square over the Young's modulus. So that's easy. Now, let's consider an additional case where now a crack has grown to a size of 2A. 2A, I just want you to remember that is a convention when we deal with cracks to actually measure or name the size of the crack as 2 times A. So A is the half length of the crack. Make sure you remember this, because sometimes that leads to numerical errors. Anyway, so what I want to actually discuss is actually try to make you understand what is the energy picture in a body that has this crack. So there are 2 or 3 points to consider. First of all, far away from the crack, there is no difference between a body with a crack and a body without a crack. This is far away from the crack. Now, at the crack tip, in front of the crack tip, there is an amplification of the stress. I would like to point out that the amplification is very local. We will see its magnitude and its distribution in the next couple of lectures, but I want you to assume that that contribution is actually very small. More important is actually a reduction of the elastic energy of the material around the crack for the following reasons. If you consider the crack and an elementary volume of the material just next to it, you may be able to see, and you need to think about it, but it's not difficult to really convince yourself that the vertical stress, in this case, if our axes are x and y, sigma yy in this part of the material close to the crack is actually 0. It is 0 because there is nothing actually here on the free surface of the crack to resist that stress. So if this is a free surface, there's no force on the free surface, that means the stress in the direction normal to the surface has to be 0. Therefore, we have a substantial reduction of the stress at this point, because remember, before that area had an energy per unit volume that we calculated here, but here it has no energy at all. And so we will make the assumption that the area, a cylindrical area around the crack, is actually free of stress. So whatever elastic energy was there before actually is no longer there, because the stresses there are practically 0. So I think it's easy to see why the vertical stress is 0. It's not easy to see why the horizontal stress is 0, although somebody may say, hey, there's no external horizontal stress. There is some horizontal stress there, but its presence is relatively small. So it is a good assumption to assume that actually this area has no energy. So what we have here is we have a transition of the material from not having any crack to having a crack of length 2a. That means we increase the energy because of the formation of the free surfaces of the cracks, and that energy that was used to create these two free surfaces came from the reduction of the stress in this volume. So by connecting these two, we will be able to understand things related to the way that the crack propagates, as we will see in a few seconds. So calculations were correct. The difference in energy should be, the difference in energy should be 1/2 sigma square over E times pi a square, but a precise analysis of the stress around a crack of this geometry actually shows that this kind of assumption is off by a factor of 2. So this estimate is a much more accurate estimate of the reduction of the elastic energy due to the presence of a crack of size 2a. And so this is the energy that is actually provided from the elastically loaded material, and that energy is actually used to create the extra surface energy because of the presence of the crack. And the estimate of that is actually this number right here. It is actually 2a, right, times T, which is the thickness of the material, so that's the thickness, right, times gamma S, which is the surface energy per unit area, times 2, because we have two sides, there are two surfaces that they are generated. So this is the energy that needs to be provided by the elastic energy. So I'm going to write the difference of the energies of the two configurations A and B like this. And so the energy in the configuration that has the crack is whatever energy the material had without the crack, right, minus the amount of energy that corresponds to the reduction of the elastic energy, plus the amount of energy that corresponds to the creation of the surface of the two surfaces of the crack. So this expression essentially it shows the evolution of the energy of the material as a function of the crack size. So as the crack size grows, the energy of this material under this stress evolves. Now, how does it evolve? Well, you can see easily that this is a parabolic equation. A parabolic equation means, and in fact, actually with a the a square term with a negative sign, which means that there is a maximum, and therefore, if you plot U sub a versus the size of the crack, you have an inverted parabola with a maximum, and that maximum corresponds to what we call the critical crack size. And I'll tell you why we call it critical. Well, if we are below that critical crack size, if we have a crack that is less than that critical size, then any increase of the size of the crack requires more energy for it to occur. So do you want to increase the crack? Fine, no problem, just give me more energy, right? This means that the increase of the crack size is not going to be spontaneous. Therefore, fracture will not occur spontaneously. On the other hand, if you are above that critical crack size, then the increase of the crack size actually corresponds to a reduction of energy. And since we have a reduction of energy, this change can be spontaneous and it corresponds to fast fracture. Therefore, this is the maximum crack size that can be sustained under an external stress sigma. Okay? Below that crack size, it doesn't matter how much the stress amplifies locally at the root of the crack will not grow. If you exceed that crack size, then that crack cannot be sustained under that stress, and therefore it grows spontaneously. And the criterion that allows us to determine this critical crack size is essentially this equation right here, which we're going to have a look at it in the next slide. Well, to see what it means, all you have to do is actually rearrange it, right? So you can take the Young's modulus and put it on that side, and you have one term that looks like this, and another term that looks like that. I will rewrite this in the next page. So I was saying that we have a pi sigma square alpha critical, right? And then on the other side I had this. Let's look at these two sides of this equation. Well, here we have things related to external load and geometry. Geometry, the overall geometry of the material, and also the geometry of the crack. And on the right hand side we have just material properties. Essentially, this is the criterion for failure. When the right combination of load and geometry exists, and they are equal to some combination of material properties, then fracture occurs. And you can rearrange this and write it in this form, for example, which says that if you have a crack size A, then the stress that will make that crack size to break is actually equal to this set of this expression right here. Okay? So these slides essentially summarize the equations that I was writing before, and you see them in a neater way, where the fracture criterion is stated clearly. What we have here is actually some terminology, some terms that you have heard before, maybe you forgot. So this part on the right hand side of the fracture equation, we call it fracture toughness. So fracture toughness is the material property that when a combination of load and geometry parameters reach that critical value, then fracture occurs. And to a first approximation, this fracture toughness can be expressed as a function of the surface energy and the elastic modulus. We will see later whether this is a good approximation or not, but for the time being, that's what it is. The term on the left-hand side, it's called the stress intensity factor. It tells us how a combination of an external stress with a specific magnitude of a crack size, how intense they are in terms of how close they are to actually making the material to fracture. And again, what I said before, this is load and geometry dependent, this is material property. Couple of things that actually it's important to know. The units of stress intensity factor and fracture toughness are this one here. They are rather strange units. They are units of stress, MPa for example, and square of length, which in the case of the common unit that we use is MPa square root of meters. KSI square root of inch is actually used as well, and in fact it happens that these two units are actually very close to each other, so one of these is one of those. The next thing that I wanted to indicate to you is actually that different crack geometries create different stress intensities, and you can see this in these two geometries, where here we have a full crack of the size of 2a, and here we have a surface crack that has a half size equal a, and in this case the stress intensity is this, as we discussed before. However, in the case of the surface cracks, there is a factor here which makes the stress intensity to be a little bit higher. Actually, this is quite interesting, because if you look at these two geometries, you have the impression that they are at least related to each other. So half of this should be equal to that. And if that's the case, then there should be no extra factor there. There should be no reason why the surface cracks of the same geometry should actually have an increased stress intensity factor. In fact, actually, what this means, this 10% higher number, it means that your a surface crack is actually more dangerous than an internal crack, because for the same geometry a higher stress intensity appears. Let's see if I can actually make an example, give you an example why this is the case. Let me actually insert an empty slide. And write a few things. So what we had before, oops, was this geometry subjected to an external stress sigma, and this geometry subjected to an external stress sigma. And in both cases, here the size of the crack is 2 alpha, where here the size of the crack is actually alpha, and in both cases alpha is actually much less than the width and the length of I meant to put it in a different way, but it doesn't matter. So in both cases alpha is actually much smaller than the dimensions of the material that is being stretched. So I was asking you to think, come on. Why this geometry here, and this half of the geometry there, why these two are not equal. In fact, I'm giving you the answer that they are not equal, but why? They look identical, the geometry is the same, the stress is the same. There is only one difference, and that difference is that we always say that surface cracks are more dangerous than internal cracks. Let's see where the different materials fall with respect to fracture toughness. Well, you can clearly see why metals are actually useful, because their fracture toughness is actually quite high. And at the very top of the ranking for the different materials, we have steels, which some steels, not all of them, that have reasonably the highest values of fracture toughness. Titanium alloys are up there, aluminum alloys are a little bit lower, and magnesium alloys, unfortunately, they are actually lower. And I say unfortunately because magnesium is a very attractive material because of its very low density, but its properties are still not really as high as the other materials. Of course, you can normalize with density and say, okay, on a normal basis, on a normalized basis is higher, but still on an absolute basis, their properties are not high. So on the other side of the low fracture toughness, we have, of course, ceramics. Don't say this to Barsoum. Yes, ceramics are really not good for fracture toughness. There is a class of ceramics, the so-called technical ceramics, that they have slightly higher fracture toughness. We have silicon nitride, aluminum oxide, silicon carbide, and of course diamond. But still, their values are actually almost an order of magnitude lower than those of metals. Similarly, polymers are not very good in terms of fracture toughness. And the compromise is that actually composites in the direction of the fibers can have very high fracture toughness, and that's why when we want to use something light, but for structurally demanding operations, we have to use uniaxial composites. So that's the range of the different properties. And these are numbers that it's good to keep in our mind. So essentially, this is what we got. Metals at the top, composites somewhere in between, ceramics and polymers at the bottom of the scale. This is actually a very interesting graph. These graphs are coming with the name of Ashby plots, and their characteristic is that essentially it's a representation of all possible materials on a map of two different properties. And in this case, the two different properties are on the x-axis we have the yield strength, okay, and on the y-axis we have the fracture toughness of the materials. And it's interesting to see that actually the metals are the materials with the best possible combination of high strength and high fracture toughness. You can make stronger ceramics, although this is a little bit tricky because actually here strength for ceramics is not tensile strength, but it's actually the compressive strength. So in a sense it's an unfair representation of their properties, but bear with me for the time being. Here are your polymers. Foams are down here, and here are some natural materials, and glasses are down here. What I would like to ask you to do at this point is actually try to remember in some of your previous classes you have heard actually that fracture toughness and or toughness, I'm not sure how much you talked about fracture toughness, but toughness in general, or for example ductility, which is sometimes used as an incomplete measure of toughness, but it's still used as toughness, that it is related to yield strength. In fact, I'm sure that in some of your classes, most probably in metals, you have seen graphs that they look like this. Toughness and strength here, that they look like this. And in fact, you have talked about the possibility of compromising, in fact, reducing the strength in order to increase the toughness. Now, what I would like you to see is, okay, if this is okay, where is this in this graph? Do you really understand what that means? Why don't we see lines and like this here? And the answer to the question is really that this kind of relationship, it's not really a relationship that holds across classes of materials, but it is a relationship that holds for a given material, and the differences in properties here the differences in properties are achieved through heat treatment, changing of the microstructure. So you shouldn't look at this kind of behavior across material groups, but actually within material groups. And if you see here, for example, the steels have a distribution like this, copper alloys have a similar distribution like this, and on it goes. So this is something that is is correct for a single material, while this is a representation of a very broad class of materials. At this point, I wanted to stop the technical discussion just to show you a couple of pictures. The use of fracture mechanics is ultimately related with the technological issues associated with the aerospace industry. In fact, the very birth of fracture mechanics was related to an accident of a military plane in the end of 1960s that essentially forced the engineers to look at things in a different way than they were looking at things before. In my personal life, if you wish, when I was a graduate student and I was taking a course in fracture mechanics back in the late 80s, this accident happened, the one that you see on the top right. It was an accident of the Aloha Airlines, where a big chunk of the airplane, as you can see in the picture, was actually fractured and removed from the plane, the pilot was actually able to land the plane. That is, the structure was already designed in a proper way, so that even with such an immense defect, the plane did not really fall off the sky. There were 2 deaths actually associated with this accident, because I believe it was a hostess and one of the passengers that was not using a seat belt, that were essentially sucked out of the airplane because of the pressure difference. So the moral of the story is not just know your fracture mechanics, but also put your seatbelt when you're flying on an airplane. The second airplane happened actually 6 or 7 years ago. I was teaching exactly this course, and then we were talking exactly about fracture and fatigue and this interesting damage occurred in a Southwest Airlines. I think he was flying to, I forget exactly where it was, but it was interesting because a similar accident as the previous one that I was discussing actually resulted in a much lower amount of damage. And going back to time, there were a lot of interesting accidents related to airplane. Some are marginally related to fracture mechanics, but they are interesting. And I included here, just for your encyclopedic knowledge, an accident related to British Airways, where essentially an improperly installed pane of the windscreen actually failed, and it blew the captain of the plane out of the aircraft. So what you see here is actually a person with his legs actually caught at the edge of the window that is open, and in fact actually co-pilot was able to perform landing while others were actually holding his feet so that he wouldn't be pulled out of the plane, and he survived. Anyway, end of the story, end of this parenthesis. There are many other examples, and if you are interested in these days, it's easy to actually Google them. All right, let's keep moving. To close this part of this lecture, I wanted actually to have a look at one of the assumptions that came, well, not assumptions, one of the approximate expressions that came out of the analysis and the discussions. And I'm referring to the estimate of the fracture toughness as it was given by this formula, which is the square root of 2 times the surface energy and the times the elastic modulus of the material, which essentially reflects the 2 aspects of the crack propagation that we have analyzed up to this point. Essentially, the creation of new surfaces, which is reflected to the surface energy, and the elastic energy, which is reflected to the Young's modulus as a source of the energy required to provide for the propagation of the crack. So what I have in this table is actually a list of materials with the corresponding numbers of the surface energy, the modulus, and the value of this expression. And since we can actually fracture materials in the lab, we can also measure fracture toughness from an experimental point of view. We can easily measure the load at failure, and that will give us a stress. And if we have a way to actually measure the crack size, and we will discuss this in detail, then we can actually estimate the stress intensity at the point that is equal to the fracture toughness, and therefore experimentally we can measure this value, and this is what I have on this column of the table. And so it would be very interesting to see whether this approximation is close to the experimentally measured fracture toughness. And I have a list of materials here that range from polymers to metals to glass. And if you go down the list, you will see something interesting here. Essentially, every number on this column is actually smaller than the corresponding number on the experimental column. And the difference is actually sometimes very large. It could be more than just one order of magnitude. In fact, one order of magnitude is the smallest difference that you will see here. Therefore, there is an issue. Although this was actually an interesting approximation from the theoretical point of view, there is a very large difference between the experimentally measured fracture toughnesses and the fracture toughnesses as predicted by this formula. There is a difference that needs to be estimated and actually justified properly, and we'll do this in the next few lectures. So just to recap what we have discussed up to this point, we have reviewed some basic aspects of ductile and brittle fracture. We talked about Sharpe test. That was the way that things have been designed for a long period of time, and we have justified its importance, and also some of the tricky aspects of this test. We discussed the concept that essentially it is the cracks that cause failure at stresses that they are lower than not just the ideal strength, but actually sometimes even the yield strength of a material. We also have discussed adequately the fact that crack propagation requires actually a source of energy, essentially a balance of energy. That is, energy is coming from somewhere, and that somewhere is actually the elastic energy stored in the loaded material, and that energy goes into, or part of that energy goes into the creation of new surfaces, at least, maybe more, and we need to understand this, and we will soon. We did talk about actual values of the fracture toughness. We talked a little bit about the fact that sometimes microstructures in the same material offer different compromises. I mean, a compromise between toughness and strength. You can go for high toughness and lower strength, or we can keep high strength and actually live with lower toughness if we can. And the last one is, I mentioned it before, that the surface energy due to the creation of the new surfaces is not adequate to justify the level of fracture toughness that most materials show. And we need to understand this because it hides behind it, this difference actually hides behind it aspects of the material microstructure that can be utilized actually to define and to design better materials with better fracture toughness.